Okay, a box with a square base and an open top must have a total volume of 108,000. Find dimensions of the box that minimize the material. So here's our box. The base is square because it's S by S. It's H units high, and a little tweak to the diagram. There's no top, which means we can see down into the box. That's going to matter in a minute when we set up our equations for it. The material required to make the box when you're building something like this is its area. The total area of all these sides is how much cardboard or wood or metal we'd need to construct this thing. So minimizing the material in this case amounts to minimizing the area. So what's the area? The floor of this box is S by S. So there's that. Each of the sides of the box is a rectangle, which is H by S. And there are 4 sides like that. So S squared for the floor, 4HS for the front, back, left, and right sides, and there is no top. If there were, I'd be putting 2S squared. So this is our total area, and we want to minimize it, which means we want to take a derivative and set it to 0. But not a good idea to do that right now because at the moment we have 2 variables, and that produces hairy derivatives that we would rather avoid. So, can we get rid of one of these variables? It looks to me like there are s's all over this thing, so probably getting rid of h is more promising as a way to go. How can we get rid of that h, or express that h in terms of s? Well, we have this volume we haven't used yet. They've told us they want the volume, which would be s squared times h, to come out to 108,000. That would mean h is 108,000 over s squared, or if you prefer, 108,000 s to the minus 2. Either one of those works. So anywhere there's an h, we can put one of these things in its place. Let's see how it looks after we do that. Our area is s squared plus 4h times s, and that cleans up to s squared plus 4 times 108 is 432,000 s to the minus 1. Okay. I went with this form because the power rule is about to happen, and so we might as well get into power form and be ready for it. So let's see what happens when we differentiate this thing. So the derivative is just dA ds equals derivative of s squared is 2s, and derivative here is minus 432,000 s to the minus 2. And all that has to come out to 0 if we're trying to optimize this thing. We want to find where the bottom of the valley is, the lowest possible amount of material. So, how do we solve that? That's not quadratic. And I mean, I'm happy to get a break from the quadratic formula, but still this thing's looking a little dire. 2s minus 432,000 s to the minus 2 means this equals 0. Any ideas? How do we isolate s in here? Well, it's super bad news that s is in 2 different places in this equation, so if we could solve that, that would be nice. And we can, because we can multiply the entire thing by s squared, as in get rid of the denominator. So we multiply this term by s squared, and we multiply the rational part by s squared, and we multiply our right side by s squared. And when we do, we get 2s cubed. Here, the s squareds cancel, so we just get 432,000. And on the right, 0 times s squared is still 0. So that was nice. We went from having s in 2 different terms to having it only in 1 term, and now the way forward is a little easier to see. If we take the 432 to the other side, we get 2s cubed equals 432,000. We can divide both sides by 2 and get s cubed equals 216,000. And I feel like s is going to be 60, but doing cube roots in one's head is not something one can do consistently. Oh, it is. S is 60. So that's a good start, but we're not done. They said the dimensions of the box, meaning the box is 60 by 60 by how much? We need the height as well. Well, good news. Along the way to doing this, we found a nice expression for the height, which says the height is 108,000 over s squared. And now we know s, so this thing is just what we needed. 108,000 divided by 60 squared tells us that the height is 30. So this box should be 60 by 60 and 30 centimeters high, and that will minimize the material required.